Hey everyone, so today we are going to be taking a look at autoencoders. Autoencoders are personally my favorite thing about neural networks and what they can do, so we're going to spend a little bit of time here. Just to give you an idea of the game plan is we're going to look at autoencoders today, and then in a future video we'll look at the derivation, the mathematical derivation of the variational autoencoder, and then we'll implement a variational autoencoder. And then we're going to look at the derivation of the vector quantized variational autoencoder, and then we'll do the variational autoencoder, the vector quantized variational autoencoder, and then we will do a Gumbel softmax, also vector quantized variational autoencoder. So we're going to look at a bunch of different, applications or different methods of doing autoencoders. We'll probably also take a look at beta VAE, but don't worry about what these terms are right now. Today we're just going to start with a simple example of what is an autoencoder. And so autoencoders are all about compression. It's all about taking data, compressing it down, and then uncompressing it back. And there's a couple good examples that we can talk about. First of all, we can, most people have heard of the MP4 compression, right? This is basically every video you take is probably saved in some type of an MP4 format. And what MP4 does is actually kind of interesting. So a video, for example, is a sequence of frames, right? It's just a sequence of images, right? It's lots of images over time. And typically you'll have maybe like 24 or 30 or 60 images every second. So that's actually quite a bit of data. And so MP4 compression asks this question. Let's say we have this picture here. This is the first image in the frame. And then we have this next image after that. And the question is, does anything change from one image to the next? For example, if there's a person talking in your picture, there's some of these parts of the image, like let's say this entire section here, some of these sections here, nothing changed. It's just the background. The person's moving in this part of the frame, which means there's portions of our image that's the same from frame to frame, which means we actually don't need to save these portions every single time. We can just save the portions that are changing. And that's kind of a general idea of what an autoencoder would do. It looks for redundant information and tries to compress it down. It's typically true that we don't really need all of the data. We just need some compressed form of it. And as long as this compressed form allows us to go back to the original data format, then we're basically good to go, right? And there's obviously trade-offs, right? Like if you are saving an image, for example, and you compress it with some format, and then when you uncompress it, the image looks like garbage, that's not a good compression type, right? It's not a good compression program. And so the whole goal here is, can we come up with smart compression methods? In the case of the autoencoder, we effectively utilize a neural network to do this compression for us. And so let's go ahead and talk about probably an example that y'all have seen before, and that's PCA, or the principal component analysis. If you don't know what PCA is, just please go online. There's great videos from StatsQuest and some other folks that have basically covered this topic in detail. I'm just going to assume that PCA is known knowledge. But just as a quick recap, the entire purpose of PCA is to take your data, find the directions of highest variance or change in your data, and then reduce the dimensionality. So for example, in this point cloud here, the direction, the first principal component, would be in this direction because we can see the data is most stretched, or there's most variance or change along this direction. And then the second direction would be this one here. But PCA has one major restriction in that each of these principal components must be orthogonal to each other. So they must be 90 degrees to each other. So that's a restriction that's in PCA. And this PCA, the reason this 90-degree situation shows up is if you look at the derivation for PCA, you're actually computing these eigenvectors on your covariance matrix, and then on the covariance matrix is symmetric, it's positive semi-definite, so it gives you these nice properties that, hey, your eigenvectors are all going to be orthogonal and your eigenvalues are all going to be positive, so on and so forth, right? So that's basically what happens. And that's why this is effectively restricted to 90-degree angles. And that's just PCA, that's just, how it works, but it seems to work really well in practice, so it's used all over the place. And now in PCA, right, one thing I want to mention, so we had x1 and x2. That was my original dimensionality of the data, right? So 2 dimensions. Each point is represented with 2 numbers. All I've done is I've created PC1 and PC2, which as you can see is basically just a rotated and shifted version of x1 and x2, but that's besides the point. It's just we have these two components, and let's say I'm training a classifier. And my classifier, I could train it on these two features, but the question is, can I just train it on one feature? And so what we're going to do is take all of our data and project it onto PC1. So we're just going to ignore PC2. So we're just basically going to project all our data onto PC1, and we get this kind of straight line here, just a single component with all of our data on it. And we would probably have just as much luck doing classification on this than we also would do here. Right? So this is effectively what the principal component analysis is doing. You will train your model, train the PCA, and then you'll just kind of get all these principal components, and then you have to decide, using the amount of variance explained, how many principal components do you want to keep for your compressed data format. Right? And that's it. That's the big idea. But like I mentioned, there's these restrictions, the orthogonality, the linearity, all this sort of stuff is kind of embedded into PCA because that's what it's supposed to do. And so AutoEncoders is basically a non-linear PCA. So our kind of template here is we're going to take a look at AutoEncoders, see what cool things they can do, and then we're going to try to implement PCA without doing the expensive eigen decomposition process that you typically do for PCA. We're going to do it via gradient descent, and we're going to prove that PCA is basically just a linear autoencoder, which will be kind of cool. So instead of performing compression with PCA, we're going to use a neural network. And basically all autoencoders take this format. You start with data, you compress it down into this low resolution format, or low dimensional format. So if you can imagine, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 inputs. And what I'm saying is I want to take these 10 inputs and compress it down into 3 numbers, right? So I'm taking a 10-dimensional vector and compressing it down into a 3-dimensional vector. So that is a 70% reduction in the data, right? In the dimensionality. But the important part is these 3 numbers need to be so meaningful that the decoder portion of the neural network can take these 3 numbers and decompress it back into the original output. And that's the key idea. The encoder needs to compress data successfully, and the decoder needs to be able to take the compressed data and then, reconstruct the output. And so our loss function, what are we trying to minimize? For today, we are just going to do a simple reconstruction loss. The output needs to be the same as the input. So there's different types of loss metrics we can use. We can use mean squared error or mean absolute error or Huber loss or any one of the other kind of loss functions. It's kind of up to you at that point. And maybe some loss functions work better for the type of problem that you're working on. Later on, we're going to get into a much more complicated example, and this is much later on because we have a lot of prerequisites to get there. But this autoencoder concept is going to be super important when we implement and reproduce the stable diffusion paper in the future, right? We have a lot of steps to get there, so that's going to be months away. But you can take a look on my GitHub right now if you already know some of this stuff. Stable diffusion is basically half implemented at the time of recording this video. I still have a bit more to go, but we'll get there later. So we have a encoder, decoder, and so all we need to do is write a very simple neural network that has some linear layers to compress and some linear layers to decompress. So the first example we're going to look at is linear layers, so linear compression, decompression, and then we're going to look at a convolution example as well. So it'll be a convolutional compression, convolutional decompression, right? So we're going to see all of that today. And so let's just go ahead and get started. Easiest way to do this is just by trying. So we need OS, import random, import numpy as np, import pandas as pd, import matplotlib.pyplot as plt, right? So there you go. We also need import seaborn as SNS for nicer plots, and then we need our regular torch stuff. So we need torch, import torch.nn as nn, import torch.optim as optim. We need from torch.utils.data. We want our data set, data loader. Actually, we don't need the data set because we're just going to be doing mnist today as our simple example. We need from torch vision, import transforms. We're going to need some very simple transforms. We need from tqdm.notebook, import tqdm. Oh, we also need from torch vision.datasets, import mnist. So there we go. And then lastly, just to compare our autoencoder to a more kind of typical the PCA approach, we're going to need our PCA as well. So from sklearn.decomposition import PCA. You could also do PCA just using singular value decomposition. But again, I'm not going to go into that right now. If anyone is interested in me doing a more kind of, I'll be doing some math only episodes, or basically videos, like when we do the variational encoder next. If you want me to do math of some of these more fundamental neural network or machine learning stuff, just drop it in the comments and let me know if that would be interesting. But for now, we're going to go with this. So we're going to do a very simple, basic neural network. Oh, actually, we need a couple other things. So we need a transform. So we need our data set. The train set is going to be our MNIST model. And I believe I already have MNIST saved at this path. Data MNIST. There we go. Oh. Right, so I already have MNIST here, so we're good to go. And we want the train is true, our training split. And we also need the transform. So what we're going to do, transform, is equal to transforms.compose. And all we need in our transformations really is to convert to a tensor, right? So we just need to convert our pill images to tensor. We're going to do transforms.toTensor. Now, one thing I'm going to add here, and this is going to be for convenience for later, so this isn't as relevant right now, but I'm going to throw a transforms.resize. And if you remember, our MNIST images are actually 28 by 28. I'm just going to lightly upsample them to 32 by 32. You'll see why later. This is mostly just for convenience and for things to work out. So we won't really care about it in the linear, but when we get to the convolutions later, it'll just be a little helpful. So all our images are going to be 32 by 32 because we've done this light resizing to it. And so we can do transform equals transform. And there's our training set. Our testing set will be the same thing. Test set train is going to be false in this one. And we can set our device right here. Device is, I know there's a GPU, so there you go, CUDA. Right, so that's what we're going to train on. And so let's go ahead and get started. So first up, we need to write our basic autoencoder. And this is a nonlinear autoencoder because there's going to be nonlinearity in it. And it'll look just kind of like this, right? We're going to have some linear layers that take our input. In our case, our input is now a 32 by 32 image. So there's actually 1024 values in there, right? So it's 32 times 32 is 1024. Before it was like 784, right? Because it was 28 by 28, but we have 32 by 32 now. So we're going to take MNIST, we're going to flatten it, pass it to the first thing, and then just do some compression, pick some, what's the intermediate dimension that we want, the bottleneck dimension that we want, and then we're going to do our decompressions. And typically our encoder and decoder are mirror reflections of each other. So whatever we do in the encoder, we'll just do exactly the opposite in the decoder. And the other thing is this bottleneck, you could technically pick anything you want. So we want to compress, for example, from 1024 down to something, some number of features, right? For these vectors. I am going to pick 2 because I can plot 2 dimensions. And you'll see why we want to plot this in a bit. But if I compress my 1024 feature vector down to just 2 numbers, I can plot that on the X and Y axis, right? So it just makes life convenient. So we're going to compress down to 2 numbers, but obviously you can compress down to anything you want. The higher the compression, right? The smaller the bottleneck, the more difficult for this training task, right? The neural network will have to work harder to actually compress your data down. On the other hand, if your bottleneck was basically the same size as the input, then it'll just learn an identity function, right? So picking a sufficiently small bottleneck is kind of crucial to ensure that the model's actually doing something of value. So that's what we're going to do. Let's just keep this as simple as possible. We're going to write a class. I'm going to call this vanilla AutoEncoder, and just like every other thing we do in PyTorch, right? Def init self, and I'm just going to pass it the bottleneck size is just 2, right? By default is what I'll set it to. And so we'll have a super dot init. Oops. There we go. Okay. And so let's first write our encoder. So self.encoder is going to be a nn.sequential. So I'm just going to sequential. I'm going to pack everything into this sequential module just to make our life simple. And in this nn.sequential, let's just write our linear layers. So this is a little arbitrary. I just picked these at random. So we're going to go from we know the input's going to be a 32 times 32 flattened feature vector, because that's what we reshaped it to. And I'm just going to compress it down to 128. And then we will have a nn.linear. We can go from 128 down to 64, and then nn.linear from 64 down to 32. And let's do the last one now, nn.linear from 32 down to our bottleneck size. But these are all just linear layers stacked on top of each other. We need to add some type of a non-linearity to this, right? So let's go ahead and do that. We can just add I'm just going to do a ReLU function, right? But you could test different activation functions to see if anything else works better. But we're just going with ReLU today to keep this as simple as possible. So there we go. We now have our encoder, right? It's a stack of linear layers that take us from 32 times 32, so 1024, down to our bottleneck size, which is this, right? We're just compressing down. That's our encoder portion. And then the decoder will just be the same thing, just going in the opposite direction. So we can do self.decoder is just going to be nn. Sequential. And all we need to do is go in the opposite direction. So we can do nn.linear from bottleneck size to 32, nn.linear from 32 to 64, nn.linear from 64 to 128, and then again nn.linear from 128 to 32 times 32. So all I've done is just go in reverse. And again, just like before, we need to add in our activation functions. So there we go. Now, one thing I'm going to be adding here is also a sigmoid activation. So nn.sigmoid. Why am I doing this? This is mostly for the purposes of visualization and reconstruction. So let's take a look here. Our MNIST images, if we just iterate, so we can run this, for sample or image label in train set print image break. If we take a look at the image.min, right, the minimum, it's a 0, right? So the smallest this can be is a 0. The smallest each pixel number value can take is 0. And if we do image.max, it's going to be 1, right? Basically 1 is the highest it can go. So I know that my images are compressed, or not compressed, but represented with numbers between 0 and 1. And so that's what I'm training on. I could also normalize this, right? So I could have thrown a transforms.normalize here, and this would have actually been even better. But let's say we do 0.5 and 0.5, right? So 0.5, 0.5. So what is this? This is the mean, and this is the standard deviation. So how do we normalize something? We take x, we subtract the mean, and we divide this whole thing by the standard deviation, right? That's how we typically normalize stuff. Well, x is between 0 and 1, right? We know x is already scaled between 0 and 1. What we're going to do is divide or subtract 0.5. Well, 0 to 1 minus 0.5, let's add some space. 0 to 1 minus 0.5 will just lead to something that's between negative 0.5 to 0.5, right? We just shifted it over by 0.5. And then if we divide this by our standard deviation, 0.5, this will lead to a tensor that's between -1 and 1, right? So the idea here is that if we do a normalization, then our data is scaled between -1 and 1. If we don't do the normalization, then our data is scaled between 0 and 1. And which one you do is completely up to you. The normalization would actually make it better because neural networks like data being centered at 0. We don't really care about any of those things right now. We're going to see more of that in the future when we start doing diffusion and like we actually care about that sort of stuff. MNIST is just such an easy example that we don't really care. But regardless, our data is between 0 and 1. So we're going to ensure that the decoder, when we generate, right, what we need to do is reconstruct our sample. So our decoder needs to produce an output that looks like the input, right? The output needs to look like the input. If I know the input is between 0 and 1, then I want to make sure the output is also between 0 and 1. And we know the sigmoid function is a great function that will scale things, or a great activation function that will scale our values between 0 and 1. That's the whole point of sigmoid. If our data was scaled between -1 and 1, like if we had normalized it, then we could have used a tan h here, right? So we could have used the tan hyperbolic. Tan hyperbolic scales between -1 and 1, but today we're just sticking to 0 to 1, so we're doing sigmoid. So if you ever see that in a model, that's why. You could also omit it. You could also not have a sigmoid. Then just when you go to plot it, then you have to do a little bit of work on clipping it and that sort of stuff. And I don't want to look at that today. We're going to try to keep this as simple as possible. So we're ensuring our decoder can only output numbers between 0 and 1. Good. So what I'm going to do now is we have to write our typical forward function, def forward self x. And in our forward function, right, we know data is going to be in the shape of, because these are images, batch by channels by height by width is going to be x.shape. We know this is how it is, but we can do x equals x.flatten after 1. So remember, channels will be 1 in this case because this is a grayscale image, and then we just want to flatten our 32 by 32 image into a single feature vector of length 1024 because this is a linear layer that expects a 1024 input. So that's all we need to do, just flatten these features, right? Just flatten them out. And so let's just take a quick example or a quick look at this. We can do model is equal to vanilla AutoEncoder, and we'll leave the bottleneck size as is. And we can do rand is going to be, we know it's going to be torch.rand, and we can say a batch size of 2. We know there's one channel, and each channel is going to be 32 by 32. So we can pass our data there, and we can print out x.shape. And there we go, right? All we've done is take our images and flatten it into a feature vector. Again, if you're a little bit unsure about this, just go take a look at my introductory series on neural networks. When we train the MNIST stuff, we do the exact same thing. We just flatten our images to pass them to linear layers. Again, flattening is not a good idea on images, right? It doesn't make sense. We're losing that spatial coherence, basically the spatial autocorrelation of the image itself, how pixels that are close to each other are correlated with each other. That information is all lost, which is why we'll be doing convolutions just a little bit later. For now, this is what we have. And so step 1 is we need to encode these images, right? So we're going to do x is equal to self.forward enc. And what I'm doing here, and this will make sense a little bit later, is I'm just going to write a utility function, just a super helpful function here, forward enc self x, and we're just going to return self.encoder x. So this way, when I want to take my data and just pass it through the encoder only, I can just use this function here, and that's all. And so that gives us what we need. But this will give us print x.shape, and we'll get 2, because we set our bottleneck size to 2. If I set this to 25, then our bottleneck size would be 25. It's just I can't plot 25 dimensions, right? There's no way for me to do that. So that's why we're doing 2, so we can actually plot it on an x and y plot. So there we go. We have that. We have all of this. We have our encoder. We have now encoded the data, right? We've compressed our data. And now our decoded is going to be equal to self.forward, just like before, DC, right? And actually, I'm going to call you encoded, and I'm going to pass into our decoder the encoded data, just so it's clear. Right, so there we go. And so just very similar, we're going to write def forward decoded self x, and we're going to first do x is self.decoder, right, the decoder that we wrote, and we can print x.shape, and it should get us back to 2 by 1024, right? We've outputted 1024 here, and because of the sigmoid, all these numbers should be between 0 and 1. So we're good to go there. Now, this is obviously not the shape that I want my data in, right? So I'm just going to do it manually here. We're just going to do x is equal to x.reshape, and we can do -1 by 1 by 32 by 32, right? So I'm just going to manually reshape it back because I know there's one channel, I know there's 32 pixels, or it's a 32 by 32 resolution, and I'm just kind of, doing the broadcast, or it'll do the batch size automatically. And we can return x. And so now our decoded, print decoded, not really decoded, but it's shape. Right, our decoded shape is back to the original image size. So this just lets me make sure that my decoder just returns things back how the image originally was. So now I can do my reconstruction stuff. And that's it. That is my entire very simple autoencoder model. And I'm going to return both the encoder and the decoder. Right? I'm going to return both of them. So there we go. Great. So that's our setup. Now all we need to do is train this model. So let's write a super simple training script here. And this shouldn't look all that different from any other training script we've ever written, but we're going to just do it. So we're going to do our model. What do we want to train? Our training set, our test set, right? So typical things. We have our batch size. We have our training iterations. How many iterations do we want to train for? Evaluation iterations. How often do we want to evaluate our model? And that should be good. So we can do print, let's just say training model. And we can just go ahead and print the model out so we can see it right here. And let's do train. We're going to give it the model, our train set, test set. Let's say our batch size is 64. Our training iterations is going to be, let's say, 5,000, right? So there we go, 5,000 training iterations. And our evaluation iterations, let's say we evaluate every 250. There we go, right? So there's our model. So I'm going to just comment these out for now. We'll print them out later just so we can not keep scrolling too much. And so just like always, we have our, we already have our device, so we're good to go there. We're going to do model equals model.to device, right? So that was the CUDA that I set ahead of time. Our train loader is just a data loader wrapped on our train set with a batch size equals whatever batch size I picked. And then our test loader is again a data loader test set, again batch size equals batch size. There we go. Now that we have that, we need our optimizer. You can pick anything you want. I'm just going to use Atom. So optimizer is optim.atom model.parameters, right? And our learning rate is going to be 0.005, whatever. They're just random. So I'm going to store train loss is here. Our evaluation loss is here. Train losses is here. So that'll store our overall results, and you'll see what we're doing. Losses is here. So we're going to store our per eval losses here, and then the overall training results in these two lists. So there we go. Okay. And now all we're going to do, we're also going to store a encoded data per eval. So we'll see what this is a little bit later, but for now, just we have that, right? So that's where we're going to store some stuff. P-bar, we need a progress bar. It's just simple TQDM, and it's going to be range training iterations, right? So there we go. That's our progress bar. And so we're going to set train as true. Our step counter is going to be 0. And we're going to do while train. So while we're in our training loop, we're going to do for images, labels, and train loader. We can do images equals images.to device. So one important thing to mention, I have labels. Notice that I'm not using them, because in this whole autoencoder process I just mentioned, I pass in an image and I output an image. There is no label, right? There's no labels in here, which means this is a method of unsupervised learning, right? We're learning from data only, which makes it super flexible, right? We can train it on lots and lots of data that we have no labels for because it's too much work to hand label a ton of data. So we have our images, right? So there we go. And what we're going to do now is encoded, and our reconstruction is going to be equal to our model, and we're just going to pass in our images. So what we should have here is print reconstruction.shape, and I'm going to throw a break in here, and I'm going to break, and then I'm going to put a train as false here just so the loop ends. So there we go. And we should see we get this back, right? So we passed in a batch size of 64, each image is 1 by 32 by 32, and that's exactly what our reconstruction looks like as well. Now that we have that, we can go ahead and compute our loss. And again, there's a lot of different loss metrics you could use: L1 loss, Huber loss, L2 loss, whatever. We're just doing L2 or mean squared error loss today. So that means we could use the torch MM or MSE loss if we want, or we can just do it manually, right? We can do images minus reconstruction squared, right? So there you go. That's our mean squared error loss. So we print our loss. We can see that is our current loss value, and we're hoping it will decrease as we train. And so what we're going to do is just go ahead and store in our train loss dot append loss.item. We're going to go ahead and store that, and we can just do our regular steps. Loss.backward, optimizer.step, optimizer.0 grad. Right? Just like always, nothing new. And now we can do our conditions. If step counter percent, here we go. If it's evaluation iterations is 0. So every 250 steps in this case, right? Every 250 steps, we want to evaluate our model. So that means throw our model into evaluation mode. We're going to create something called here encoded evaluations. You'll see what that is in just a second. And we're just going to loop through our data for images, labels in test loader, right? So we're looping through our testing data now. Just like before, images is images.toDevice. We're going to put it on the GPU. We're going to do encoded reconstruction is equal to our model images. Our loss is going to be, again, torch.mean. It's going to be a mean squared error between our images minus reconstruction squared, right? So there you go. That's our simple loss. And we can go ahead and store in our evaluation loss.append loss.item, right? So nothing crazy. And here's the important part. I want to just store the compressed data. So I want to store the compressed evaluation data. So what I want to store is these encodings because I want to actually visualize them later. So let's take a look at that. Print encoded.shape. I'm going to throw a break in here. This should show up. There we go. So I have compressed my data, my 64 samples, from the 1024 vector that they started with just down to 2 numbers. And I want to store this so I can actually visualize it in the future to see how our model organizes the data in the latent space. And that's the important part. So let's go ahead and store that. We're going to do encoded, and labels is going to be encoded. Let's move it off the GPU. So we can do .cpu. And we're going to flatten. In this case, there's nothing to flatten, so it'll just be 64 by 2. When we do the convolutions, we'll have some extra dimensions, so we're going to flatten on 1 just to make sure we flatten everything out. So there we go. Flatten 1. And our labels equals, our labels is going to be labels.reshape, and I'll just make it a column vector. So -1, 1, and you'll see why we do this later. And so what I want to do is if we print encoded and print labels, right, you're going to see that here's my encoded samples. So for the first sample, these are the 2 numbers I picked to represent it. Second sample, these are my 2 numbers I used to represent it, so on and so forth. These numbers are garbage now because the model hasn't trained anything yet. And here are the corresponding labels that go with all of them. So I'm just going to concatenate them together. I'm going to add another column here with these labels, right? So all I have is my 2 numbers and their corresponding labels, so I can do some cool visuals later on. So we're going to go ahead and do that. We're going to do encoded evaluations.append, and we're going to append on what? Our torch.cat, and we're going to concatenate on our encoded and our labels along the last axis. So we can do axis equals -1. So we print encoded evaluations. Let's just print out the first one, dot shape. This should give us a 64 by 3. Right? And if we look at the actual data itself, it's just those original samples. And I've concatenated on the class label for each of these samples, again, for future visualization. So we are good to go here. And what we want to do is after we've stored up all of these, so this is for every single sample, I'm storing in this list, it's encoding, so for every batch, right? So that's for the batches. We're going to go ahead and do our encoded data per eval. So for this full evaluation, I want to do .append, and I want to store torch.concatenate, right? Torch.concatenate encoded evaluations and .detach, right? We don't want it to be a part of anything. So all I'm doing is basically this here is per batch, right? So I'm storing in this thing basically a list of batched these, right? So we'll have this for the first batch, this for the second batch, this for the third batch. I just want to take all of the batches of these and concatenate them all together into just one big tensor. And that's what this is, right? This is me concatenating all those batches together to make just one big one of these, lots of rows. And then I'm just taking it off the computational graph because we have no reason for that. And actually, I should also throw a with torch.noGrad right here just to make it as correct as possible. So now that we have that, we should be good to go. And so we can now store, let's just do some housekeeping. Our train loss, right, is going to be np.mean train loss. And our evaluation loss is again np.mean evaluation loss. And we can go ahead and store train losses.append train loss, evaluation losses.append evaluation loss. And now we can just go ahead and print out our loss just so we can see what's happening as it's going. So print training loss, that's our train loss. And then again, print our eval loss, that's our evaluation loss. And there we go. That gives us everything we need. And lastly, we just need to go ahead and do our train loss is now back to an empty list, and evaluation loss is back to an empty list. So we're just resetting the lists so they can, basically, I created these two empty lists up here to populate for every evaluation. I'm just going to reset those lists to empty so I can, again, begin repopulating them. And I believe that's all I need there. And then otherwise, right, so once all of this is done, so once we've done one of these, we've completed a step. So we can do our step counter plus equals 1. And we can do p bar dot update bar, var, dot update 1, right? So we're going to update our progress bar, just like that. And last check, if step counter greater than or equal to, greater than or equals to training iterations, right? So once we've trained for 5,000 iterations in this case, once we're done, we can do print, we can say completed training, and we can do train equals false, right? Turn it off so it'll exit the while loop, and we can throw a break in here, and this will be over, right? So that will exit this while loop, and we'll be done. And now that we have that, we can go ahead and do encoded data per eval. So this is basically after training is completed. So let's make sure we tab out one more here. Once training is completed, all of these encoded data per eval, these are all tensors, which is fine, but let's just go ahead and convert them to numpy arrays. So we're going to np.array I for I in encoded data per eval. So we're going to go ahead and store all that. Hopefully I spelled everything correctly. And then we will go ahead, everything else seems to be fine. Yeah, so we can go ahead and just return everything. So we're going to, all we really need to return is our model, train losses, evaluation losses, and our encoded data per eval. Right, so we're just going to return everything back, and we are done. So we can put U2 back. Let's just test this for 5. Let's do 100 here and 25 here, just to make sure this works, make sure there's no bugs. Yeah, good. So training is happening. Oh, it's printing stuff out that I don't want to. Let's see here. What am I printing that I don't want to? I am printing out the model. Okay, let's check. We want, okay, so let's double check here. When I run this, it is printing out training, but then it prints it out. Oh, of course, right. So that we need to first do model, train losses, evaluation losses, encoded data per eval is equal to all that, right? So we're just going to go ahead and store that, and we are done, right? So, it's not doing the last 25. Let's see. Well, it's probably just an indexing thing. It's fine. So let's go ahead and make this. What did I do? I did 25,000, and I evaluated every 250. So let's see how long this will take. Okay, just a minute, right? So no problem. What you should start to see is the losses decreasing. And we do see that, right? 0.39, 0.3, 0.38, 0.37, 0.36, so on and so forth. So our model is is indeed learning something. Something is decreasing. And it started with like 0.2 at the very start. So we should be good to go here. What I want to do is actually we need to redefine the model. So we're going to actually do model is going to be our vanilla autoencoder with 2 as our bottleneck size. So there we go. That'll start with a fresh model. So 22, 27, 4, ... So it's going to train. Won't take very long. And so while it's training, let's go ahead and just write the plotting function for our things. So what I want to do is just plot the embedding space. So as you can imagine, our encoded data per eval, right? We're storing this every evaluation iteration. And so what we have is what we saw earlier. We have 3 columns. The first 2 columns is the X and Y coordinate of where the model decided to place those embeddings. And then the third column is the class label. So we're just going to leverage that. We're going to write a function here called def build embedding plot. And we're going to pass it a encoding. And we're going to pass it a title that we want to give this thing. So there we go. And so we're going to do encoding is equal to pd.dataframe. Right, so I'm going to convert this to a pandas data frame. So it's just a NumPy array right now. We're going to convert it to a pandas data frame just to make life a little bit easier, because we can use group by and stuff like that to plot it, and class. This needs to be our encoding. And our columns is equal to these 3 things. Right, so those are the 3 columns. We have 3 columns. We had a X coordinate, a Y coordinate, and then its corresponding class label. Right, so we have all of that. And I'm just going to go ahead and do encoding is encoding.sort values by equals class. So we're going to sort our whole thing by class, so we have that. And we also need to make sure that the class label is some integer. So we saw it stored as float. I could have done that earlier as well, but let's just make sure it's an integer. So we're going to do encoding class is just going to be encoding class, and we can do dot as type int, and then as type type a string. So we're going to make sure they're strings. This is just so we can easily use them as a label when we go to plot it in our thing. So it doesn't really matter. It's just for the plotting function. So we can say our model is completed training, right? So model is done training, which means we have this variable now called encoded. Oh, whoopsie daisy. Let's go back up. We have this variable now called encoded data per eval. We can take a look at it. It's just this. It's just a list of all of our compressions. And what we want is the last one. So basically the final one that we worked on. And notice that it's basically a column of labels and then our X and Y coordinates of where it decided to place these embeddings. And so there we go. And what we're going to do is, so yeah, let's just do this. Build embedding plot. And let's give it a title like AutoEncoder embeddings. Right, so there we go. And so if we display our encodings, because it's a data frame, encodings, encoding, sorry. This is our data, right? Or basically what we're working with. We have our class labels, 0, 1, 2, 3, up to 9, and we have their corresponding X and Y coordinates. And so let's just go ahead and plot this data. So we are going to do for grouper group in encoding dot group by class. So we have to plot every class individually. So we're just going to do that. We're going to loop through all of them. And we're going to do just a plt.scatter, right? Just a simple scatter plot where X is going to be the X column of the group. Y is going to be the Y column of the group. And the label will be the grouper. So the grouper will be 0, 1, 2, like so on and so forth. It'll just be the class label. And I just for visualization, I set the alpha to a little bit lower, so 0.8, and S is 5, so that's the size of the dots. And then once all this is done, we can do plt.title, our title that we set, plt.x label is going to be X, that's our X coordinate, plt.y label, that's our Y coordinate, and then we can do a plt.show, and I think that's it. And this is what our compressed data looks like. So notice we have some evidence of clustering here. So if we do plt.legend, it's not going to look very good. It might just, oh, it looks fine. So here's our legend. Notice how it's self-organized. We have like the ones, for example, are all right here. The twos, this green, is kind of all right here. The sixes are kind of here. Notice that 4 and 9 are very close to each other. So notice the blue and then the purple underneath it. They're basically overlapping. This makes sense because this 4 and this 4s and 9s look kind of similar to each other, right? They look very, like perceptually, they look very similar to each other. And we, again, lost all of that, the actual like autocorrelation between the pixels because we flattened them as feature vectors. So as far as the model is concerned, we can see the 4s and 9s are just very close to each other because they can't really separate them apart. The zeros are kind of over here and so on and so forth. So we have some organization here that's happened in the latent space. And this is effectively the latent space of the model, the compressed representation of our model. And that's basically what's popping out of the encoder, which is really neat to see. So now that we have this, we can look at it for, let's look at one of the earlier ones. So when it just started training, right? At the beginning of training, notice that there was no self-organization, right? So there you go. If we look at one, and this is really the neat part about autoencoders, it actually does kind of what PCA does. Notice how it's first, so first example, let's go back again. Actually, let's just do a loop. This is going to be terrible. We're going to do for I in range len encoded data per eval. This might print out like 50 things, but that's fine. We can delete it after. We're going to just print out for every single I. Here we go. So we start with this kind of random point cloud. The model hasn't learned anything yet, hasn't organized anything. First, notice that it stretches things out in one direction. This is almost like principal component analysis, right? In principal component analysis, we're looking for a component that is explaining the data in the maximum direction of variance. Well, here you go. I'm stretching the data out in one specific direction. After that, notice it's starting to stretch in another direction, the second principal component. And you kind of see this fanning occurring, and it starts to self-organize, right? So you can start to see all of our data splitting up, and you know, it looks really cool. And as it's training, it'll continue to organize. Notice here, like the orange, for example, is this big point cloud over here, right? Kind of this region, and the blue is kind of this region. As we continue to go through the training, notice that it starts to consolidate itself again. So be more structured and efficient in its self-organization. And this is just a really, really cool way to interpret autoencoders. They may not be exactly what's happening, but it's the way I understand it. So, and it seems to help me out when I'm trying to understand like what I'm attempting to do. So this should give you everything you need. All we've done now is train a very simple autoencoder. Nothing crazy has happened. I'm just trying to relate it a little bit to PCA, and that's it. So I'm gonna go ahead and get rid of this. So that's it. This is it, by the way. Everything you need to know about autoencoders, you already have now. And what we're gonna do now is just look at kind of different iterations of this autoencoder. So first, I want to look at the relationship between PCA and a regular autoencoder, right? And that's it. So I'm going to just copy, actually there's no reason to do this, we can just do it, class linear autoencoder. So this autoencoder is just going to be 2 layers. It's going to be super simple. We're going to do def init self, and then we're going to provide it some bottleneck size, right? So bottleneck size, again, it's 2 by default. And our self.encoder is just going to be a nn.linear with 32 times 32 in, going straight down to our bottleneck size. So there is no activation functions, there's no nonlinearity. It's just a simple projection onto our data, onto the to the lower dimension data. And then our self.decoder will be exactly the same thing, nn.linear. It's going to take bottleneck size in, and it's going to output 32 times 32 out. So, right, so it's just a simple linear layer to compress, simple linear layer to decompress. And what I want to see is what is the relation between this model and something that PCA would do by default, right? So that's our goal. And so our forward function will look exactly like before, def forward self x, and all we need to do is x is x dot flatten 1, just like we did earlier, right? So we're going to flatten our data because they're images. X, or our encoded is going to be self dot encoder x. Our decoded is going to be self dot decoder the encoded data. And then we just need to make sure our decoded is in the same shape as the original data, so we just need to reshape it back. So let's do that. So our decoded is going to be decoded.reshape, and we know it's going to be -1 by 1 channel 32 by 32. Right, so there we go. And we can now return our enc and decoded. So very, very simple neural network with just 2 linear layers, and that's all that's happening here. Let's go ahead and train it. Training it will be identical to earlier, so we can just grab u. And we'll just have to change the model, right, that we're training. So we're going to put you right here. And what we're going to do is use the linear autoencoder as our model, right? So let's go ahead and run this. Looks like I missed the super, like I do every single time. Super.init does not have a, I spelled decoder wrong too. Nice. Decoder. And we're off to the races, right? So it's going to train whatever it does. Now, what I want to point out while this is training is let's pull up PCA, a visual of PCA again. Let's see if I can find a good one. So let's do this one. We get excited of that. So here we go. We have a visual of principal component. It's basically what I showed earlier, right? Nothing new. And the important part is this. When we're doing principal component analysis, you actually do PCA for all of your things. So if you start with 2 dimensions, you will compute up to 2 principal components. If you started with 1,000 dimensions, you will have 8,000 principal components. And so me going from my original data to the principal components is actually just a simple linear projection or a linear layer. It's just a linear. It's a very simple linear operation, right? Just multiplying by some weight matrix to project. Now the thing is that if you use the full weight matrix, you'll project from your 1,000 dimension to your 1,000 dimension, right? So if you start with 1,000, you'll use the full, full weight matrix, the full transformation, and you'll just, project everything, and that's fine. But if you only use a part of that weight matrix, like the first 2 rows or the first 3 rows, or however many you use, then you end up with a lower dimensional form. Like I'm saying, I only want the first 2 components, the first 3 components, the first 4 components, however many you want. And so that's it, right? So we just want to replicate this very similarly with what we're doing. Instead of training an entire neural network to go from 32 times 32 to a full 32 times 32, we are just going to compress straight to 2 and go back up to 2. And we're going to take a look at this in just a second here. So here we go. Training has occurred. Let's go ahead and compare this to PCA. So I want to plot this. So let's take a look. And I didn't call it that, so let's call it, again, encoded data per eval. And there we go. We kind of have this point cloud going on. Let's look at the first one, right? If we look at the 0, again, it's randomly kind of just, nothing's really happening. 1, we start to see it stretching out in one direction. 2, stretching out more in that direction. Let's skip ahead. Let's go to 10, right? Stretching out more. 100, there's probably not that many. Let's do 50, right? It's exactly what we saw earlier, right? It's just happening for the autoencoder. So what I want to do is compare what we just had here with our principal component analysis, right? So the regular PCA. For this portion, I am just going to copy this data because what I did here is not really of interest to y'all. It's really just the results of what we have. So I'm going to copy this code. Nothing is happening. This is just me applying PCA to my data set. I just had to convert all of my data in my test set or whatever to a big NumPy array, have the labels, and then apply PCA to it. And I already had this, so this won't be linear data anymore. This will be encoded data per eval. And then I have some side-by-side plotting, so nothing crazy. And here you go. Do you see some similarities between these? These look almost the same. I mean, the PCA just looks rotated like by 90 degrees, right? Clockwise. But these look very similar. Like we have the same structure of the oranges and the blues. We see the gray is kind of underneath there. We have the pink right next to it. We have and the blue kind of stretches out on the top. These look very similar to each other, and this is exactly what I mean by we can use a simple linear neural network as an approximation of PCA. And as evidence for this, I want to take a look at the actual embeddings, right? So let's actually do this. So we can look at PCA. So we trained a PCA model. So when you actually do PCA, this PCA, you can do .components, and it will show you the two principal components that we decided to keep. And it's as simple as that, right? Here are my two principal components. These are basically my projection matrices. So these two things combined, if we look at the shape, .shape, this is 2 by 1024. So this is a matrix that takes a 1024 dimensional vector, like our original data, they're 1024, and compresses it down to two numbers. And that's it. So it's a 1024 to 2 projection. That sounds like what we did, doesn't it? We did a 1024 to 2 projection, right? That's my encoder. So these matrices should be, this should basically remind you of that, right? That's the big idea. So we have our 1024 to 2. And so what I want to do is take a look at them. So we're going to grab the first one, so 0. There we go. And we're going to do PCA components 1, right? We're going to grab our two components. And this is basically going to be our PC1 and our PC2. I've grabbed my two principal components. And I said that these components should be at 90 degrees to each other. So let's verify that. So let's convert them to tensors, torch.tensor. We're going to convert these NumPy arrays of these basically weight matrices to tensors, tensor. And what I want to do is compute the angle between them. So to do that, if you remember, let's actually pull it up. Dot product similarity. If you remember, our dot product is actually just cosine similarity. So here's a good visual for that. Oh, come through. There we go. Right, so our dot product, A dot B, is the same as multiplying by the norm of A times multiplying by the norm of B times the cosine of the angle between them. So we can take the dot product and then just take the cosine or the inverse cosine, and that'll give us alpha. What we want is alpha. So we can do A dot B and then do cosine inverse of A dot B to get alpha, because our A and B in the case of PCA are already unit norm. So they actually already go ahead and do the unit norm for us, so we can go ahead and leverage that. So we're going to do torch dot dot, torch dot dot. We're going to take the dot product between PC1 and PC2. PCA dot components. There we go. So that is my, and this should immediately ring flags, right? The cosine of 90 is 0, right? The cosine of 90 is 0, but we can verify that. We can do our torch dot a cos, so our inverse cosine, that computes this, but this is in radians, which is not helpful for us. So we can do torch dot rad to degree, right? We're going to convert our radians to degrees. And there we go. We can see the principal one, the first principal component, and the second principal component are at 90 degrees to each other. And this only worked because our principal components are by default from PCA already unit norm. So we don't have to worry about them. What we need to do is, and we actually, let's double check that real quick. If we do torch.norm of PC1, we should get 1. Yeah, so they've already gone ahead and unit normalized these weight, basically the weights. In our case, in our network that we trained, we don't actually have them as unit norm, so we need to make them unit norm, and that's pretty easy to do. So we're going to do model weights is going to be, let's just extract from our model.encoder, so we can look at our model weights. That's our encoder, and we want it for this linear layer, so we can do dot weight, right? That's how we get the layers. And so here are my two projections, right? Or my two linear layers, or basically our weight matrix. So if we look at the shape again, dot shape, the same 2 by 1024, right? It's our weight matrix projecting a 1024 down to a 2. So it looks very familiar to earlier. So we have to perform the exact same strategy that we just did earlier. We're just going to have to do it for our weight. So we're going to do weight vector 1 and weight vector 2 is going to be our model weights 0. And we're going to make sure it's on the CPU. I think it was already, but just in case. And then model weights 1, again, CPU. The thing is that if we do torch.norm wv1, right, we can see these are not unit norm vectors because they don't technically have to be. These are learnable parameters. We never put a restriction on them that they have to somehow be unit norm, right? So, but we can just unit normalize them ourselves. So let's go ahead and do that. To unit norm something, all you do is just divide something by its norm. So we're going to do weight vector 1 is going to be weight vector 1 divided by its norm, right? That'll unit norm it. And then again, weight vector 2 is going to be our weight vector 2 divided by torch.norm weight vector 2. So all I've done here is go ahead and unit normalize my weight vectors. There's no reason for it other than if we didn't, then we'd have to like divide by it because, you know, we want to take the inverse cosine and just use that, basically do what we did up here. So it's easiest if they're already unit normed ahead of time so we don't have to worry about it. Again, we can double check torch.norm weight vector 1, for example, and we can see now they have been unit normed. And so what we want to do is compute the angle between these. So that's just this again. So we can use that. But now it'll be between weight vector 1 and weight vector 2. And we can see it's 80 degrees. So like I mentioned, it's not perfect. It's an approximation, but it's close to 90, right? Like it's getting there. Maybe if we train for longer or, you know, did something else. In my example case, when I was working on this notebook earlier, I actually set a seed and I actually got 87 here, right? So fairly close, right? Pretty close to what we want. And we can see these embeddings look very similar to each other, right? So either way, this is just further evidence that I'm trying to provide that autoencoders and PCA are trying to do very similar things. It's just that autoencoders can add nonlinearity, because if we look at the, first of all, we can have many linear layers with nonlinearity between them, in which case we can't really do this type of analysis anymore because there's no relationship between a, you know, the earlier autoencoder we wrote with all the ReLU activations and stuff like that and PCA. But either way, we kind of get this, you know, some cool tidbits, right? That's all it is. It's just to provide some intuition for this stuff. And why do we like this? Because if you remember in linear regression, right? In linear regression, if you already know, the formula for the weight matrix is actually directly computable for linear regression. It's x transpose x inverse, x transpose y. Ta-da! You have your linear regression optimization formula. The problem is x transpose x inverse, that matrix inversion is a very expensive operation for large data sets, and you want to avoid it, right, as much as possible. In the same way, when we do PCA, there's basically two ways you do it. You either do the eigenvalue decomposition of your covariance matrix, or you do singular value decomposition on your mean-centered data. Those are your two options. Either way, eigenvalue decomposition or SVD are both expensive operations, right? And so again, we can leverage things like neural networks to iteratively get an approximation of PCA via gradient descent. Not that neural networks aren't expensive, but they're expensive in a more manageable way, right? Because we have ways to accelerate it with GPUs and stuff like that. So either way, this is basically our wrap up for linear autoencoders. Now let's look at convolutions. So something we haven't seen yet actually is a transpose convolution. So we have seen convolutions, and if you remember, let's kind of remind ourselves with these. Let me find those GIFs actually. Convolution, transpose, convolution GIFs. So I really love these figures because it makes things so nice to understand intuitively what's going on. So we've talked about convolutions in quite a bit of detail already. If you don't know, I have a whole video on Intro to Convolution. I will link it here, I guess, if I don't forget. So I'll link it here. And you can go take a look at that and you'll have a better understanding of exactly what convolutions are, what its significance is in signal processing, and some of the methods we use to accelerate convolutions using GPUs. But for now, it's fine. I'm assuming convolution is already known knowledge to you. Okay, so we have this convolution, and if you remember, convolutions are compressive feature extractors, right? So the input has some shape, and we kind of slide a filter along it, and we compress our data down. That sounds perfect for our autoencoder, right? We take our images, and we compress it down into some low resolution representation. The deconvolution or the transpose convolution is exactly the opposite. It takes a low resolution image and attempts to upsample it, right? It attempts to upsample it to our original image space, or basically, add additional resolution. So transpose convolution is a popular way of upsampling things. So there you go. There's a couple different variants, as you can see, like there's dilated transpose convolutions and so on and so forth. We're just going to stick to simple ones today. So we have a convolution and we have a transpose convolution. And we're not going to look at too many details of the transpose convolution other than just getting it to work today. When we implement the UNet a little bit later, we will kind of sink our teeth a little bit more into some of the stuff in transpose convolutions. But all you need to know is a transpose convolution takes a lower resolution image and upsamples it. So let's actually do a quick example. Let me just find it. Maybe it'll be helpful to add some necessary context here. So I want to look at the UNet implementation that I had. Let's see here. Okay. Yes. Okay. So let's do this. So what we're going to do is just a quick example of what transpose convolutions are before we keep going. So we're going to create a rand tensor. Let's say rand is torch.randn, and we're going to do a 2x3. So 2 input, 2 samples, 3 channels, and each image is, let's say, 64x64 just for now. And let's define a convolution. Our convolution is going to be nn.conv2d, right? It's going to have an in channels of 3, so in channels equals 3. And let's just say the out channels is 3 for now. So we're not going to really deal with the channels because we don't really care about the channels right now. So out channels is also 3. So we have the same input and output channels, just keep those the same. And let's do a kernel size equals 3, stride equals 2, padding equals 1. So if you know, stride equals 2, padding equals 1, 3, 2, 1 on these kind of factor of 2 pixel resolutions will always lead to a halving of your image space. So we should go from a 64x64 down to a 32x32, and we can check that. We can do conv_rand.shape. And we can see we have basically halved the resolution. We went from a 64x64 down to a 32x32. So there we go. Now that will be our encoder, right? The encoder is going to stack a bunch of these convolutions together, downsampling by factors of 2. The decoder now needs to do the same thing, but it needs to upsample by factors of 2. And so let's take a look. Let's do the inverse convolution. So I'm going to call this tconv transpose conv nn.conv transpose 2d. So it's a transpose convolutions, conv transpose 2d. Again, in channels is equal to in channels 3, so 3. Out channels, so I'm going to leave it as 3, so channels is 3. So that stays the same. And what we're going to add is a kernel size, right? Kernel size. Let's just do the same. We're going to do a kernel size of 3, a stride of 2, and a padding of 1. And what I'm hoping is if I apply a transpose conv to my convolve, I'll get the same thing. But unfortunately, that doesn't work out. Because notice how we went from a 64x64, we went down to a 32x32, but when I upsample it, we're only at a 63x63. Why does this happen? Well, this is because when we do convolutions, there's actually a floor function. So it actually rounds. So if we look at our nn.conv2d formula in PyTorch, so we can take a look right here. Notice that the output shape, they give you the formula for the output shape. There's actually a floor function. So multiple input values can lead to the same output value. So for example, if we try it, let's create 2 tensors. I'm going to create rand tensor 1 is going to be torch.rand, And we're going to do, again, 2 by 3 by 64 by 64. And we're going to create another one. Rand tensor2 is torch.rand 2 by 3 by 63 by 63. Right, so there we go. And what I want to do is print our convolution that we had earlier applied to rand tensor 1. We're going to print out the shape. And then we're also going to print the convolution on rand tensor 2 dot shape. And notice here that regardless, so notice how this is 64 by 64, it gets compressed to a 32 by 32. But this is a 63 by 63, and it also gets compressed to a 32 by 32. So in the downsampling, because it's a floor function, they're all basically rounding down to 32 by 32, which is fine. But when we do the transpose convolution, it doesn't actually know. When I go from 32 by 32, I can go up to either a 64 by 64 or a 63 by 63, and it doesn't know which one that it needs to go to, right? Because either one are valid possibilities. So by default, it goes to the smaller one, which makes sense, right? It just goes to the smaller one. But if we want to add a way for it to not go to the smaller one, we can add this extra parameter here called output padding, and we're going to call this equal to 1. And that gets us up to the 64 by 64 that we need. Basically, there's just some uncertainty about which resolution we want to upsample to. So it's, again, it's basically this, because multiple resolutions can lead to the same downsampled shape. So when we go from downsample and upsample it back to our transpose convolution, it doesn't know which one. So we can specify which one by basically adding these extra output paddings, which makes it now a 64 by 64, which is exactly what we want. Let's go ahead now and do it. So this gives us, again, this is just a quick primer. We'll look in more detail into these transpose convolutions when we implement UNet later. But for today, this should be sufficient, I think. So let's go ahead and do class convolution, convolutional AutoEncoder, nn.module, definite self in channels. So we know these are MNIST images, so they're going to take one input channel, and then we're going to do a channels bottleneck, and you're going to see what this is in a bit. So we're going to see what that is. So we're going to do self.bottleneck is equal to channels bottleneck, and we're going to have self.inChannels is equal to in channels. Right, so there we go. And so let's go ahead and do our encoder. So self.encoder conv is nn.sequential. And the reason, so this goes back to why did we do a, if we go to the very top, why did we reshape our image to 32 by 32? It's because downsampling becomes convenient, because I can go from a 32, downsample by a factor of 2, and now I'm 16. Downsample by a factor of 2, now I'm 8. Downsample by a factor of 2, now I'm 4, ... So it's obvious what it should be. If we left it at 28, it still would have worked fine. So if I downsampled by a factor of 2, it'd be 14. And then I downsampled by a factor of 2, it's 7. But if I wanted to downsample again, this is like, it could be either 3 or 4. Like there's some uncertainty, and it would still be fine. You could still work with it. You just have to like add, just be extra careful about it. And I am too lazy for that. So we are just making it a easy factor of 2, just so everything stays simple. And this is why when you see those like big generative models, like diffusion models and stuff like that, they're always in factors like 256 by 256 or 1024 or 512. They intentionally stay in factors of 2 just because it makes life simpler, and a little bit of interpolation is no problem at all. So we now have our encoder convolution. Let's go ahead and write it. So this will be nn.conv2d. And our do in channels is going to be channels is 1. Or it's going to be in channels, our variable. And our out channels, let's just say it's 8, right? I'm just coming up with stuff. And we're going to do a kernel size is 3, stride equals 2, padding equals 1. And there we go. And then we're going to add a batch norm, right? That typically helps, so we can do that. Batch norm. And this will have 8. And then we will do nn.reloop. And there we go. Now, one thing to actually keep in mind is when we do batch normalization, and this should actually be batch norm 2D, because it's a 2D batch norm. When we do batch normalization, it's going to recenter, right? So it'll center it to 0. which means if we had a bias here, this bias will be immediately normalized out in our convolution. So you can imagine, like, if we had x is equal to y plus 2, and let's say x was between -1 and 1, that means when we add 2 to it, it'll become -1 will become 1 to 3. But then when we normalize it, it's just going to go back to -1 to 1 again, right? Basically, we want the center to be at 0. Well, to make 1 and 3 to be centered at 0, we just have to subtract 2 again. So if we subtract 2, then 1 and 3 will just go back to -1 and 1, which means this plus 2 has effectively just, removed. Like it never was actually included. We never did anything with it, which means if we ever follow a convolution with the batch norm, we can actually just go ahead and just do bias is false, because the bias parameter just immediately gets removed by the normalization when we just recenter to 0. So there we go. So we don't really care about it. So we did one of these, and we're just going to do like 3 of them. So we're going to do now in channels will be 8, out channels will be 16, and then in channels is 16. Out channels is self.bottleneck. Bottleneck, yeah. So basically we are deciding our bottleneck in the case of our linear layers was basically, how many numbers do we want to project to? So we started with a 1024 and compressed down to 2 numbers, right? In the case of convolutions, typically we define our bottleneck by the number of channels, right? So basically how many channels do we want to use? So we see that our model went up to 16 channels here. But every time we increase the channels from, this should be 8, increase the channels from 1 to 8, 8 to 16, 16 to whatever, we also are downsampling the image by factors of 2 every single time. So we're getting more and more channels, and we're getting smaller and smaller resolutions, which is a typical kind of structure for convolutional neural networks anyway. At the end, we're just going to say that we want only 4 channels, and we know that there's 3 downsamples here. So it's going to downsample by 2, 4, 8. So it's going to be a factor of 8 downsampling, which means our image that's 32 by 32, it's going to go from 32 by 32 down to 16, down to 8, and then down to 4. So in the end, we should end up with a 4 by 4 by 4 cube of data basically right here. Right? So we'll have 4 channels, and each channel is going to be a 4 by 4 resolution. And we'll see that in a bit. So now that we have this, let's just kind of create a tensor, test it out. So we're going to do rand is, again, torch.rand. And we know our data is going to be, let's say, batch size by 1 by 32 by 32. We know that's what it's going to be. And our model is our convolutional AutoEncoder. Just like that, we'll leave the defaults. And we're going to write our def forward self x, right? And in our forward function, we're going to do exactly what we always do. Batch size by num channels by height by width is equal to x.shape. Just store those variables. So I don't think we actually need them, but whatever, they're there. And our encoded data is going to be self.forward enc. Actually, we're going to write our forward enc, def forward enc self x. And when we encode data, very simply, we're going to do conv enc is going to be self.encoder conv x return conv. Right, so there you go. We're not really using these helper functions right now, but we'll need them later for things. So I'm just trying to keep everything as similar as possible. Just like every single time, I always forget super.init. So there we go. So we have that. What I want to do now is pass my data into my model. So we're going to do model rand. And what I want to do here is print enc.shape. And it looks like we have a bug. So we have running mean should contain 16 elements, not 8. So that's because this out channel is a 16, so this should be 16. And then this one is self.bottleneck, so this should be self.bottleneck. There we go. So like I mentioned, we downsampled a 32 by 32 by a factor of 8 because we have 3 downsamples of factors of 2. So it's 2, 4, 8. So our 32 by 32 goes down to a 4. And our number of channels is 4 because I set my bottleneck channel to be 4. So now what I'm doing is representing our original data. The original data was 32 times 32. We're representing 1024 pixels with a 4 times 4 times 4 tensor. So we've downsampled from 1024 numbers, right, pixels, to a 4x4x4, so just 64 numbers. So I'm using 64 numbers to represent my 1024 numbers. And you could do higher compression factors as well. You could add more downsampling. I could pick less, like more of a channel bottleneck. So I could do 2 instead of 4 here. You can play with it, right? It's fine. You can do whatever you want, but we're representing every single one of these as 64 different numbers. So every image is represented by 64 numbers. Now you may be thinking, like, Priyam, how do we plot this, right? There's no way we can't plot 64 numbers, and we'll see how we can do that in just a bit. Actually, we'll probably see that next time. So I'm not going to go into that today. Well, basically the idea is we can leverage TSNE to plot these things. Maybe I'll just throw it in. It's not in my existing notebook, but maybe it's good to see. So we'll see in a bit what that looks like. For now, let's just keep going. Our decoded is equal to self.forward decoder x, and then we return decoded and encoded. Encoded and decoded. There we go. We need to write the forward decode. So def forward decode self x. And all we need to do is x equals, no, this is fine. So we can do return self.decoder. Actually, we never even wrote the decoder, so let's do that first. Yeah, so we're going to do decoder con x, and this is where we're going to test it out. So self.decoder conv is nn.sequential, sequential. And just like I mentioned, we want to upsample by factors of 2. So to do that, let's kind of just do this the dumb way. Well, we'll just do one at a time and just check the shape for imprint. Decoder.shape here. So nothing has been done yet. So there we go. I'm going to get rid of this so it's not printing a bunch of stuff out. So this is where we're at right now. Right. So we're going to do let's see here, model decoder. Right. So our decoder needs to be taking the encoder. So that's where we're starting. 2x4x4x4. Good. So our first convolution is going to be nn.transpose con2d. Right, so our transpose convolution, and it's going to take in channels. It's going to be self.bottleneck, right? So whatever our bottleneck was, and our out channels will be channels is just going to be 16 because I went from bottleneck to 16 here. So I'm just going to follow the same pattern: bottleneck 16, 16, 8, 8, 1. Right, so we're just going to follow the exact same pattern. And now the important part: we want a kernel size is 3, and stride is 2. Stride is 2, and padding is 1. If I do this, so it looks like I messed something up. Transpose, sorry, it should be transpose, transpose 2D. Okay, looks like it went to a 7x7. So again, this is that discrepancy that we talked about earlier. Like it should be 8x8. Which means we need to add that output padding equals 1. And this basically gets us to the 8x8 that we want. So because there's some discrepancy in the convolutions. There we go. And everything else is the same, right? We're still going to do the same bash norm, same relu, just like before. And this bash norm will take in 16 channels. And we're just going to rinse and repeat, right? Do this over and over again. So we're going to do it 3 times because we have 3 of them here. The next one's going to take 16 in and output 8. And the next one's going to take 8 in and output in channels. And so this should be 8, and then this should be in channels. And our output here, instead of relu, we're going to do a, actually, first of all, we don't need to, remember, our data is scaled between 0 and 1, so it doesn't make sense to normalize to have a center of 0 ahead of time. So we're going to get rid of this. Because our data, if we had the 10H, then it would probably be fine if we scaled between -1 and 1, but we don't have that right now. So we're going to get rid of that. And we're going to do nn.sigmoid here for the same reason earlier. Right, we're going to make sure our data is between 0 and 1. Looks like I'm missing some commas, or all the commas. So there we go. Oh. Comma, comma. And there we go. We're back to our original shape with these 3 transpose convolutions. So we are now good to go. We can do our enc and dec, or return enc and dec. And that's our data. That's our model, and we're good to go. So let's go ahead and train this model one more time. So we're going to do our conv model This is all fine. I think I called it convolutional, AutoEncoder. Everything else is correct. So we can go ahead and run this. And yeah, this shouldn't take very long to run. So while this is running, I do realize that in my existing notebook, we never really talked about, or we never actually plotted this. So let's just go ahead and write a quick function that will do that. So the problem we have right now is our data is compressed to 64 numbers, not just 2 numbers, right? So we could plot 2 numbers. We could even plot 3 numbers if we wanted, but most conveniently, we could only plot 2 numbers. We can't plot anything anymore because, well, how can we if our, how can we plot anything if we have 64 numbers, right? So we need to do some type of compression. And so options are, we could either just do PCA on our convolutional encoding. So I basically further compress it down to 2 numbers and do it that way. That would be okay, but actually the best way is using something known as TSNE. So TSNE is a T-stochastic neighbor embedding or something like that. Again, there's a great video on this online, I believe by StatsQuest, that'll explain it. Maybe we'll implement it later because it is a fun algorithm, but it effectively, the high level idea for TSNE is you calculate the distance matrix between all of the different points in the high level, in the high dimension space, and then you compress the data down such that the distribution, basically the KL divergence, is not all that different between the high dimension and the low dimension, so that kind of distance relationship remains the same regardless of which dimension you're at. I'm not going to go into more detail than that. We're just going to directly use it, right? So we're going to train a TSNE model to further compress our data down. So how we're going to do this is our conv, actually we need to do from, I think it's sklearn dot manifold import TSNE, something like that. So if that's wrong, we'll see in a bit. How much longer do you have left? Almost done, right? So almost done training. You can see the losses, nice and small. I don't know how it's going to look until we take a look later. But for now, let's just go ahead and look at our conv AE encoding, right? So our autoencoder, what we want to look at is our conv AE encoded data per eval is I think what I called it. So let's see here. We have our conv encoded data per eval, and we just want the last one, right? The last one. And we're going to do what we have always done. So we're going to do our, if we look again, conv AE encoding, or this is going to be from sklearn.manifold import TSNE, right? We have some, oh, why is it all 0? Let's see here. I guess it is the MNIST images. Well, let's just double check. Let's do, we want all the rows and we want all the columns except the last one. Let's just take the mean real quick as a sanity check. Okay, no, there's some numbers in there. Okay, let's just, let's go with it. Let's see if it worked out. What we want to do is conv AE features is just going to be our conv AE encodings, and it'll just be that, right? We have everything but the last thing. There we go. And then we'll have conv our labels is going to be conv AE encoding, and it's just going to be that last row. So this will be everything but the last one because the last column is our labels. And then we can do TSNE is going to be TSNE. We want 2 components. N jobs is -1. You can use all my CPU cores. And so we can do conv AE compressed is tsne.fit transform x equals conv AE features. Right, so there we go. The rest of this stuff is of less interest to you, so I'm just going to copy it in. This is just converting our data to the basically that data frame that we had earlier. And then I can just go ahead and just copy paste the plotting function as well. So for grouper group in, let's just see what this looks like. Conv AE encodings is not defined, so it's encoding singular. So let's see what this looks like, if it looks reasonable. Otherwise we'll have to go back and check on our model. Let's give it a second. So yeah, while that's happening, what we're hoping to see is better separation, right? Because we did a convolution, we're looking for better separation between our different classes, because that would indicate, a successful, successful learning. And so actually, to be completely fair, we probably should not have this ReLU in here, right? Because this last, we actually shouldn't have either of these here. This last convolution's goal is to basically project to the latent space, right? And we're effectively restricting what the latent space could look like here. So ConvAE labels, because I just called it labels. So it already ran this. So let's just comment U out and let it do the rest. Oh, whoops. Okay, it's doing the fit transform again. My bad. All right, that's fine. So I think everything else is correct. We'll just let that keep going. Yeah, we probably, so this is just something to think about. We probably don't actually need these two things right here because it just doesn't make sense to project it that way. Like we're effectively restricting the latent space to just be positive, which doesn't essentially make sense and is probably why a lot of our latent space values are close to 0, right? Or they are 0 because the ReLU effectively killed them. So we might have to just retrain the model with that fix in there. But let's just see what the results look like. Oh, still running. All right. So yeah, it's compressing away. Okay. Let's just give it a second. Oh, still another bug. ConvAE labels. Let's see, labels dot reshape -1, make it a column, and let's get rid of these. AX is not defined because we just want to do plt.scatter. There we go. So we can start to see some representations, right? We have slightly better representations being learned here. It can be better, right? So let's try retraining again, but let's get rid of this stuff here, right? We don't want to restrict our latent space in any way. So this last linear layer or convolution layer should just be our projection, which might help a little bit with how it organizes. This is again for the same reason when we did our linear layer earlier, right? Our linear model, like here, it just ends with the linear. We had no more activation functions after the fact, right? So we can give this a second. This is honestly not as interesting just watching. So let's see here. We have to run U as well. So we're going to let that train. Hopefully we'll see the, yeah, so we're seeing the loss now going much more. So before it was stuck at 0.10 or basically 0.1 or something like that earlier, probably because we were having that problem in the latent space. So I do need to fix this in my Git repo. I'll get to that later. But either way, you can see the general idea here. Things are training. We probably don't even need to train as long. So let's just do, let's do 5,000 iterations instead, right? So we don't have to wait as long. Let's give this a second. And then again, we're going to rerun U on our newly encoded data. So these are kind of the things you need to think about, right? Like if you want to have any type of restraints on the latent space, and when we do the variational autoencoder in the future, you're going to see that we actually put a Gaussian restriction on that latent space, which is really neat. It basically turns our neural network into like an explainable statistical model almost, right? And we'll see that soon. Either way, let's let this run. While that's running, there's one thing I do want to mention, and this is kind of your how you think about these autoencoder models. The encoder's job is to take data and compress it down. The decoder's model is to take the compressed data and reconstruct, which means you can actually treat these models in two different ways. Number one, I can use this model if I just use the encoder. Typically, we just care about the encoder. So once we're done training, we just toss the decoder. And the encoder exists to compress my data down into some lower resolution latent space that's representative of the original sample. On the other hand, what if I throw away my encoder and I pass in some values to my decoder? So I give the decoder some numbers. Won't that generate new samples? And that's exactly what it does. The decoder is a generative model. It can take in something and create something. But what we pass in is completely up to us. And we're going to basically do that example right now. We're going to take a look at what this generative model might look like. Look at the nice separations, right? Looks pretty good. So we have these nice separations between our different classes. This is again because convolutions are much more powerful in doing this type of learning than linear layers would be, right? So there we go. We have our convolutional autoencoder. Sorry, we kind of went on that aside fixing this, but either way, it's still interesting. So hopefully that works. Now, what I want to do is right now, honestly, this stuff is not as interesting to y'all. So I'm just going to run it and just plot. This just to create some plots. So what I'm going to do is grab a, I don't think I called it vanilla model. So let's see what I called it this time. We called you our vanilla autoencoder. Okay, well, I should have actually named things better so those models existed. But honestly, it's okay. We can just look at, the important part is the visuals, and we can just look at those without me having to run anything, because there's no new code here. It's just me running stuff. So let's just take a look. First of all, this is a plot of the reconstruction. So I wanted to see, given the 7, right, what does the autoencoder's reconstruction look like versus the convolutional autoencoder? And what you can see is pretty clear. The convolution has a slightly sharper image compared to the vanilla. Like we can see the edge detail and stuff like that is better maintained. And that just makes sense, right? Convolutions understand that pixels that are close to each other have higher correlation with each other, and it doesn't lose the spatial representations like the linear layer does. So the idea that the convolution is somehow sharper just makes complete sense, right? So we have this sharper convolutional image. But the question is, can we generate a new image? And so the idea is this. What I want to do is I looped through, this would actually be relevant for us to do. So just give me a second. I'm going to rerun this notebook and I will be right back. All right, we're back now. So I didn't change anything. All the code is the same. I just retrained our original linear autoencoder and just named it vanilla model, just so we had that variable. So now we have our 2 models. We have our vanilla model and our convolution model. And what I did is I grabbed a specific sample from it, right? So whatever this is, I grabbed a sample, gave it to the model, and I kept the reconstruction just so I could plot them. And this is what they look like. And like I had mentioned, the vanilla autoencoder, typically leads to slightly blurrier images compared to our convolutions. So that's fine. What I want to do now is basically look at generating brand new images. So let's say this is what our latent space looks like. This is just a screenshot that I took, but let's say this is what our latent space looked like. So that means all of my 1s have been projected to this space, and all of my 2s have been projected to kind of this line. All of my 3s were projected here, 4s were projected wherever the purple is, so on and so forth. So things have been projected to their specific locations. And what I want to do is, okay, if 1 is represented by this whole area, kind of this whole orange region, what if I take the average or the median of this orange region and pass that median to my decoder? Will it generate a 1? And that's basically what I'm trying to ask. So let's go ahead and give that a try. We're just going to do this for the, we're going to do this just for our linear autoencoder, just to keep it simple. We could also do it for the convolutions. It just requires more effort, so we're not going to do it there. And I called this encoded, let's see here, encoded data. We have that right down here. So I called it encoded data per eval, just like before. So we have our encoded data, right? And we're just going to store the final encode right here. So we're going to start right here. We're just going to grab the last one. So we have final embeddings. These are all of my encoded data, right? Nothing fancy. And if we do our build embedding plot, and we can provide it our final embedding and our, let's just call it plot, whatever, right? And final embeddings, right? So there we go. That's what our plot looks like. So what I want is the median of the 0s, the median of the 1, the median of the 2s, ... We're going to do the median of every single class, and then we're going to pass that median embedding into our decoder model. And that decoder, we're basically just going to plot what that data looks like once we're done. So how we're going to do this is average, let's say average digit digit embeddings, right, is an empty list. We're going to do for I in range. We know it goes from 0 to 9, so for I in range 10. And we're going to do average embeddings is equal to, and we can do our, first of all, we can do final embeddings, and we want only the first two columns, right? The actual data itself. And we only want this where our, actually, first of all, we need to filter by the rows, right? We want only for the specific digit we're looking at. So we want, let's say, only 0. So we want final embeddings 2, right, or colon 2. So because the third column, or index 2, was our label column, and we're going to say that's equal to I. And if we print this out, print average embeddings, let's just break it right here, equal I. There we go. We basically have all of the rows that went with label 0 only, right? So I've just filtered it out, and I don't need the 0 anymore. I just need the first two columns, so we can just filter it out, all the rows and the first two columns. And there we go. And all I need to do now is find the median value. So we can do np.median. We could also try the mean, but I saw it worked better with the median. So we're going to do median. And this would be the overall median. So we just want to add a axis equals 0. So this is my median embedding for my digits, for my digit 0, right? So that's my median embedding for the entire digit 0. And what I want to do now is store all of these embeddings for each of these images. So we're going to do average digit embedding dot append, right? We're going to go ahead and store all of them up. And all we need to do now is pass this into our model. So we're going to do average digit embeddings is equal to torch.tensor np.array. All right, these are lists, so we're going to convert them to arrays. np.array average digit embeddings. And it'll look like this, average digit embeddings. Oh, there we go. So these are my average locations for each digit, and we can actually check that. I shouldn't have gotten rid of it. So we can do build embedding plot final embeddings, and we can just give it a name wherever, it doesn't matter. Right, so there's our name. And so we can see 0 is at roughly 0.5 and 4. So is that true? 0 is this right here, and we can see it's roughly at 0.5, and most of the density is right here. So yeah, it's probably close to 4.8, 4. So we can see it's roughly 5, right? So roughly 5.5, right? That seems about right, right? So it's close, right? So that's what we're looking for. And we just have these numbers for each one of these clusters, basically, these groups. Now, remember, our model, our neural network, the encoder compressed down to these two numbers, right? Whatever's shown here. And the decoder takes these two numbers and decompresses back to the original image space. And so what I want to do is exactly that. I just want to pass my average embeddings, or my median embeddings, into the decoder only and see what it produces. So we can do pred images is going to be vanilla model dot, and we just need the forward deck, right? So we only want to decode our average digit embeddings dot, and we can just stick it on CUDA, right? So there we go, pred images. And so these are my predicted images. And if we do dot shape, there we go, right? 1 by 32 by 32. So all I need to do is now plot these images, and the plotting function is something I don't want to write, so we'll just paste it in, right? So I'm just going to loop through every image and just create the images and see what they look like. And there you go, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it looks like our linear model struggles to differentiate between 4s and 9s, and it struggles to differentiate between 5s and 8s, which kind of makes sense because they look kind of similar, right? So these are our median generations, basically, from our autoencoder. So that's kind of cool, right? So we can see that the decoder can be used as a generative model. But there's a little bit of an annoyance when doing this. How do I know? Remember, all of this is supposed to be in an unsupervised fashion. I don't have any labels. So if I don't have labels, I can't just go and just compute the medians of my latent space. And what if my latent space is super complicated and some super high dimension? Like if we just did the convolution example, for example, we had a 4 by 4 by 4 tensor and we have lots of them. So how do I exactly do this? Is there a better way? And this is what I mean by the vanilla autoencoder latents, right? The regular autoencoder we've looked at, this is called an uncompact space. Notice that it kind of like stretches out and like we have these big like bulb areas and it kind of fans away, but there's no rhyme or reason to the construction of this latent space. It's just placed however the neural network wanted it to be. And so that's a problem, right? We can't reliably generate from this space because I don't know where it is. Again, I can visualize it here and have an idea, but if you have a super high dimensional latent space, like we will when we do latent diffusion and stuff like that in the future, we can't really explore this, right? There's nothing I can do. I mean, you could do a search method, but imagine searching over a 1,000 dimension space, right? It would take forever. So this is not a feasible method. So we need to add some type of a restriction to our latent space. And this is exactly what the variational autoencoder does. So what I did here is I wrote a function that basically spans from -4 to 4 and then -6 to 4 or something like that. So I'm going to basically sample a bunch of points from my data, just kind of in a range. In this case, we're going to be sampling from here. So we'll be sampling from maybe -5 to 20 and then -15 to 10. So we're going to pick a grid of points and we're going to plot what the reconstructions look like at these grids of points. And this will give a good idea. So this code is basically what we had done earlier, but now I've just created a grid of points, right? So I've created this grid of points that's between, in this case, we want to do from x from -5 to 20. So let's do -5 to 20. And then we want y to be from -15 to 15. So let's do that. -15 to 15. We're just uniformly sampling points along the space just so we can see what the generations look like at those different points. As you'd expect, points that fall inside the blue area should look like 0. Points that fall inside the orange area should look like 1. The points that fall inside the green area should look like 2. So on and so forth. But what about all the points in these blank areas, right? These like blank white regions, or inside, like between these pockets, like these basically pockets of air between these different regions. What happens there? And that let's take a look. So if we run this will take just a second because the plotting has to like loop through a bunch, but you get basically something like this. So we get some good constructions, right? We get our 2s here, we get some 0s, we get some 1s, we get some 3s, we get some 8s. So we get some good looking reconstructions, but we also get some of this basically failure cases. Like, what is this, right? These look like bad generations. These look like pretty bad generations. These look like bad generations. And so we have these holes in our data, basically pockets of failure inside our data where the generations are not good. And so this again happens because our space is uncompact. And the reason I'm mentioning this so much is this is our motivation to move towards something known as the variational autoencoder. So I'm just going to show you the visual right now, and we will be implementing this in a future video. So if we compare, we'll also get to VQ-VAE later, but I don't want to talk about this right now. If we take a look, this is our uncompact space of our autoencoder, right? There you go. It kind of fans out and has all this stuff. Notice our variational autoencoder is nice and circular. Most of the data centered at basically our middle, right? Most of our data is kind of accumulated in the center, and it fans out as you go out. And this should remind you of a Gaussian distribution. This is basically a 2D Gaussian distribution where most of our data is in the middle, and our data kind of, there's less data as we go out towards the edges. So if we look at 2D Gaussian distribution, you will see something like this, right? This is a very typical visual from Wikipedia, right? You have most of your data in the middle, and it kind of fans out as you go to the edges. And we're doing exactly this, but on our latent space. So the entire purpose of the variational autoencoder that we're going to look later is we want to compress our data down in a meaningful way such that our latent space is Gaussian. And the reason we want it to be Gaussian or standard normal or whatever you want to call it is because I know everything I need to know about Gaussian. I know all the properties about Gaussian. I know where the center is. I know how the standard deviations spread out. I know everything I want to know about Gaussian. So as long as our latent space is roughly Gaussian, sampling from this latent space is much more convenient. I don't have these weird pockets of space. I don't have these like weird loops. I don't have this uncompacting. Everything is nicely contained inside this latent space, and we can leverage that to our benefit. So I'm going to call it here, right? So again, just as a quick recap, what we did today is basically talk about, let's pull back up. Where did it go? Yeah. We talked about autoencoders. They're a very powerful tool that we're going to be leveraging a ton as we go forward, especially as we get into more complex models. There's a bunch of different variants of autoencoders. We're going to be looking at autoencoders, variational encoders, vector quantized variational encoders. We're also going to look at the masked autoencoder. We haven't done vision transformers yet, but that'll basically be an extension of that. Autoencoders brought to the kind of the era of transformers. And once we have all of that, you basically have what you need, right? Autoencoders are awesome. They're my favorite thing to kind of study because you get these really neat visuals about them and it makes them very intuitive, I believe. But again, if you have any questions, comments, concerns, drop them down in the comment section below. I will see you in the next video.